Okay, everybody ready to get started? So let me take a couple moments to finish lecture 1, and then we'll move on to lecture 2, okay? So the last technique that I wanted to mention was cars. So some of you may use this technique throughout your graduate career. This is going to be of these kind of introductory. This will be the one where I won't go into depth on the lectures. I had to make a cut somewhere, but I wanted to at least introduce it, okay? So it's coherent anti-Stokes-Raman scattering, and really it's a 4-wave mixing process. So really what that means, it's using different lasers at different wavelengths that cross at a point, and then they generate another actually laser-like signal, okay? So let's talk about what we mean there. So what there happens to be, there's essentially 3 beams that have to come in. There's a pump beam, a Stokes beam, and a probe beam, okay? And I've given them all different omega, okay? And the pump and Stokes beam, really what happens, it's that energy difference, right? Because if a frequency is an energy, okay? And so the pump and Stokes beam excite a Raman coherence, okay? That's just another way of saying it excites a certain allowed transition. And then the probe beam, which can be a 3rd wavelength, but it's typically the same as the pump beam, quote unquote, reads them out. And it's this 4-wave mixing process that generates a coherent laser-like beam. So I'll show you a schematic in a minute, but you send essentially 3 beams in and a 4th beam comes out, and that's your Cars signal, okay? And so for an example, let's say we have a pump and probe beam at 532, so we use a YAG output, and then we tune our dye laser to 607 nanometers. Again, we have to tune it to a specific wavelength because we need this this quantity, this delta omega here, to excite a specific coherence. What is our Cars signal beam going to be? Well, again, like I said, our pump and probe are the same. Okay, they don't have to be, but this makes it a very simple calculation. So we have 2 times the frequency. We've gotten rid of the constants here, 1 over 532 and 1 over 607. But the Cars process will generate a 473 nanometer beam. Okay. So the first thing we see, if we do this right, we're going to get a wavelength out. We're going to get a beam out at a specific wavelength, okay? But what we're also going to get out is at a specific position. The reason is the 3 beams, the pump, the Stokes, and the probe, they have to be arranged at specific angles. So they have to conserve momentum, photon momentum, okay? And so this is a quantity known as phase matching. And so right now, these are the wave vectors. We'll talk about wave vectors in a little bit. But again, what you can happen is that this is just a generic configuration of the pump and probe beam, and then you end up having your Stokes beam, and you get your Cars beam. So what this actually is quite nice is that not only does the Cars signal come out at a different wavelength, it comes out at a known angle, which means you know where it's coming out, and you can easily capture it and separate it from the other signals. And so again, a configuration that's commonly used is something called a boxcar. Here's your pump and 2 pumps, but pump and probe coming in green at a specific, you set them up in lens such that the conversion process gives you your angle. You send in your Stokes, it's coming in also at its angle, and then what you find is your 4th Cars beam comes out at a specific angle, but then when it's collimated, it's just separated spatially. Okay? So it's actually quite nice. How do you generate a Cars spectrum? Well, generally you have pump and probe at, say, narrowband 532. If you have a broadband dye laser output and you scan over these, right, as you scan the pump over the probe, there's going to be many combinations between the wavelength that's contained in this bandwidth and this pump band that actually satisfies the Raman coherence, and you end up generating a Raman spectra. Okay, that's it very simply. The most common application of Cars is thermometry. You measure a spectra, and then you essentially fit it to very well calibrated and well-known codes, and you can generate a temperature, okay? And so really kind of the summary here is that Cars is a non-resonant technique, okay? It is a non-linear technique, okay? And the signal scales is I squared. It's somewhat spatially resolved, but really the resolution is limited by the fact that you have these multiple beams crossing, okay? So we call it a single point technique, but this kind of interaction can be as large as a millimeter or so, which is not great for turbulent combustion research. But still, the information you get out of it is quite nice. It's probably the most accurate gas phase thermometry approach. You can typically get what you would see accuracy defined based to calibration flames as 1 to 2%. You actually can measure species concentration as well, major species like N2 and O2 and hydrocarbons. The setups are complex, as we can just demonstrate there's multiple lasers, and again, and perhaps at times spectrometers. It really depends on the configuration you're doing. But one thing I wanted to mention is that recent advances with these short pulse techniques really give very high signal levels, okay? And this has actually allowed extensions to 1D and some actually to two-dimensional imaging. There's some, all the past couple of years, some very advanced work coming out of Sandia and the Air Force Laboratory that has shown these extensions with these ultra-fast systems to 1D and two-dimensional imaging with cars. So it's kind of exciting. Okay? The reason why you want to go to these short pulses is they're essentially insensitive to pressure. As I said, the pulse length is so short, it's less than the collision time scale, and therefore you don't have any kind of collision effects. So you don't get any dephasing or anything that's a function of pressure. So again, really where people are selling this is it opens up a lot of new possibilities in realistic environment. Okay. All right, so the way that this lecture ended, or ends, is that really I want to emphasize before we move on, there's a large number of laser diagnostics used in combustion environments. We're going to focus on approaches that are mainly applicable to single-shot measurements in turbulent flames. In general, we're interested in characterizing the flow field, temperature, species, concentrations, reaction rates. And that's what we're going to talk about. We have to use different diagnostics to gather information that we want, okay? There's no one-size-fits-all diagnostic. They each have their own challenges. They have their own accuracies, their own resolution. They have their own degree of quantification, okay? And so what we're going to do is we're going to, in the remainder of this course, we're going to kind of extend on this lecture where we reviewed some common approaches, we highlighted the aspects, but now we're going to go in depth, okay? All right, so in about 30 seconds, we'll start at the beginning. We'll start with Maxwell's equations. We'll start light as a EM wave and classic and physical optics. And then we'll move on to instrumentation, okay? And so at this point, I'll see if there's, I talked to a few of you at the break, but maybe I can take a minute or two if there's any questions on what this lecture was before we move on to lecture 2. If not, I'll move on, all right? So that certainly feel free to find me at any break. All right, so now, lecture 2. So this is light and optics. And so for many of you, this may be a review. There's going to be a lot of elements in here that can span for some of you back to high school elements, and some of you may have never seen any of these. It really depends on what you had in different types of physics, okay? And again, this isn't a physics course, so I'm trying to give, hopefully, an overview of where the interaction of light and matter comes from. Okay, so let's start. Okay, so the goal is to provide a background. We're going to discuss geometric and physical optics, ray tracing thin lens formula. Many of you have seen these. Maxwell's equation, which provides a general framework for light propagation. Background and foundation fundamentals of lasers. We'll talk a little bit more about detection equipment now, a little bit deeper level. So let's start. What is light? Light's an EM wave. It's an electromagnetic wave. We know that EM waves are described by their position in the spectrum. We're pretty familiar. We've talked about things going from the ultraviolet down to the infrared, but we know that there's radio frequency all the way through gamma ray, and these are always kind of like, that shows the size of the wavelength here. We're going from anything atomic nuclei to football fields, depending on what that's the spacing in between the two crests of the wavelength. But our diagnostics typically in combustion research will go anywhere between the ultraviolet regime through the infrared, okay? Laser-based diagnostics in the infrared are typically absorption-type techniques, although there are some PLIF techniques that have been used. But the majority of our scattering processes will stick right in the visible, although we certainly can go into the ultraviolet regime, and then the majority of our fluorescent processes are in the ultraviolet regime. Okay, so we need some definitions that are going to be used in this lecture and throughout the remaining. We have the speed of light in a vacuum, speed of light in any material. Again, that's something that has a refractive index that's not unity. We can get the relationship between the two speed of lights just based on proportionality to the refractive index. Same thing, we have the wavelengths in both a vacuum and a medium. Now, here's where we can get a little confusing when we say the word frequency. We'll start with, again, frequency here. This is in terms of hertz. We also have the angular frequency in radians per second, and we'll have a spectroscopic frequency in terms of wave numbers. Okay? And then I'll actually later in the spectroscopy section introduce another version of the spectroscopic frequency that's nu tilde, but I'll describe that when we get there. Okay? We need to understand that light has a bandwidth. This is important. There's no such thing as monochromatic light. And so we get this relationship between frequency and bandwidth. Okay? And this will come into play in a little bit. But right now we're just kind of introducing some of these topics. Now, one thing I want to point out on as we start moving forward in Lecture 2, in some of the lectures you have and versus the final set of lectures you'll get, there's going to be equation differences between what's here in terms of numbering and what you have. Okay? They're typically only offset by a number. And that starts in, I'll tell you when that starts. That's about Lecture 6 and 7. Okay? The reason is I added new material for you, and that pushes the equation numbers. Whatever you get all new lectures at the end of this, so you don't have to worry about making too many notes. And if you're worried too much about following along too much on the equations, then you're going to miss kind of what we're talking about. So just keep that in mind. You're going to get a final set of lectures, so we don't have to worry about it. Okay? It just made me think because this is the first time we're going to see an equation with a number. Okay. All right. So light. We can describe light propagation in two ways. What's referred to as classical optics and modern optics. And modern optics, we're not going to talk about here. Modern optics really takes kind of a quantum mechanical point of view from optics. We're going to stick with classical optics that's then further divided into two branches, geometric optics and physical optics. Okay? Geometric optics is probably what you saw, whether high school, undergrad, or what even you use now when you say, okay, I have a focal lens of certain focal length, where do I put it in relation to the test section? We'll do that. Those treats light as a collection of rays. That's it. Light travels in straight lines and homogeneous, and when you have media that have two different two materials with different refractive indexes, the rays bend. Okay? That's really what happens. They're governed by laws of reflection and refraction, and essentially the level of energy is not important. It's just how do you get a ray from one place to the other, and it's really governed by Fermat's principle, which we'll talk about. Okay? This is the primary interest is when we're dealing with things like focusing, magnification, kind of that level 1 of optics. Okay? How do you set things up? Okay? Physical optics now treats light propagation as a wave. And that's where we'll spend a lot of this lecture in the form of a wave equation, okay? And again, we actually have to have this to be able to describe interference, diffraction, laser propagation, etc. And the solution here is described by Maxwell's equation. Okay, now what we can say is that geometric and physical optics are dually applicable when the wavelength of light is much, much smaller than the size of optical elements. And so really what happens, you can, for many applications, not all, you can use geometric and physical optics to get to the exact same answer. Okay? One just may be easier than the other. All right, so let's start very simple. Again, this may be a review for some of you. Fermat's principle, this is the basis of refraction, reflection. All of the possible paths connecting 2 points in space. Of all the possible paths, the light travels along the path that requires the least time of travel, not distance. Okay? It's the time of travel. Okay? And this is actually going to be an important phenomenon for actually designing lenses as well. So again, let's keep this in mind. If we're going to connect 2 points, it has to be the path that requires the least time of travel. Okay? This principle underlies laws of reflection, refraction, and optical lenses. So I'm going to skip the first example that you have, and we're going to go ahead and go to refraction. Okay? So let's look at refraction. Let's say we're sitting at point Q, and I want to get to point P. And everyone has seen this. This is exactly how you do refraction. Okay? But so let's think about it. If we want to go from Q to, if we want to go here, this essentially is just going to be a distance divided by velocity, as all time is. Okay? So let's look at this geometrically. This is the hypotenuse of this triangle. That's what we have here, and it's divided by the speed of light in this medium M1. And then this distance right here is going to be a hypotenuse of this triangle, okay, which is d minus x, and again b. Okay? Right now that's just peeling off pure geometry. Okay? So let's take the derivative of it, dt dx. You take the derivative, you get this expression. We also can recognize that this angle, both theta 2 and theta 1, the sign of those can just be written out in this way. These are just geometry. These are just using triangles. So we can get what the signs of the angles are. We can substitute in, okay? And what we can do first is if we say Fermat's principle implies that the light travels upon the points are connected when you go the least amount of time, well, that means dt dx has to be equal to 0. Say it's a minimum. So we set this equal to 0, substitute our signs, and you end up with this expression, which is the well-known Snell's law. Okay? So all this was a very simple example to show you Fermat's principle. You can do the exact same thing. It's in your booklet in terms of reflection. You actually can do reflection in a way here using triangles as well in geometry, and you always get to the correct laws. Okay? But we have to introduce Fermat's principle because we'll use that in our lens, in designing lenses. Okay? We also need a quantity called the optical distance. The optical distance is defined as L times C naught over C, or L times N. Okay, what is L? L is the physical length L, okay? And L naught is the distance that light would propagate in free space and the same time it takes to propagate through a medium that has a certain refractive index. So let's say I have a distance L, and it takes a certain amount of time to propagate through that. L naught is the length that would be longer or smaller in general, but longer in a vacuum. So it goes the exact same. So if I'm going through the sludgy material that's short, I have to go through a much longer material so that I end up at the point at the same amount of time. Okay? So this is the optical distance. Okay? Propagation is time. This is the key. The propagation time is the same for all rays traveling through the same optical distance. So it doesn't matter what the real distance is. Okay? And the reason why we're going to do this is this tells you the shape of a lens. And let's see if we can pick that out quickly. Well, we know the goal of a lens is to collect radiation. So we have light at O, and we want to image it on I, or we want to transfer it to point I. We know that the rays emitted at O are in a cone with solid angle omega naught, and they're imaged at point I with omega I. Okay? Well, we know from Fermat's principle that rays emerging at O can only intersect at I if their propagation times are identical. So we know that they need to be there at the exact same time. Well, we know that clearly the rays that have to travel here and here travel a much longer geometric distance than the ones going right down here. Okay? So really, we kind of need to slow these ones down in the middle. So they have to go through a material with an index of refraction greater than 1 for a much longer distance than the ones at the edge. And so the only way for them to end up at I at the exact same time is for the optical distance, or the optical distances to vary within the cone. Okay? And so that's how you get this kind of lens shape. Okay? You end up with thicker along the axis compared to thinner, such that all these rays, no matter where they go to the lens, ends up at the point at the exact same time. Okay? Otherwise, you can't reconstruct an image. Okay? Now, if we really want to manufacture a lens, we need a lot of complicated parameters. We need detailed characterization. But if we want to describe them, if we want to do something, say, useful in the lab very quickly to design our optical system, we just really need the focal length. So the focal length is going to be related, well, we're going to relate them to these two distances. So we're defining them right now as S naught is the object distance. This is the distance from the center of the lens to the object, and the same way we're going to have an image distance. So if we have a lens to our reconstructed image, okay? So again, if we take a very simple schematic, let's look at this. We have our object O, we have our image I, we have S naught SI, okay? Now, in order to do our quick analysis, just getting our brains thinking of optics, again, we're going to use the paraxial approximation, which really means that, again, S naught, if you will, the object distance is much, much greater than essentially the size of the lens, such that we have a small angle here, and that all of the rays lie very close to the axes, okay? This allows us to do a lot of small angle approximation, okay? And in the same way, now this represents the schematic of bringing stuff from a point O. Now if we have a finite object, this is essentially how we're going to transfer that information to an imaged object. Okay? So what we have to do is rely on the fact that, again, we have an object distance, we have an image distance, and again, we have our focal length here, F, and then we have the inverted image as well. Okay? So all we're going to do is a little bit of geometry on this. This isn't the main purpose of this lecture, but I just wanted to show it that if we use an analysis of similar triangles, you can work this out on your own very quickly, I think. If we just use these the similar triangles, really all I want to get to is the fact that a very useful formula actually in that I mean we use daily to set up optics is the thin lens formula. Again, I know I skipped through like 4 there, but it's just algebra, and so it's just using geometry and then substituting in, okay? But really, if the lens is thin, what you end up is with 1 over the focal length of the lens is equal to 1 over the object distance minus 1 over the image distance. And I'm sure many of you have seen this, and this is actually even what you work with. This is what, even though regular lenses have a certain thickness, if we're setting up in the lab, whether it's a camera or a lens to focus laser, we always start with just the thin lens formula, set everything up, and then make adjustments where needed, okay? So this now relates these parameters. Okay. We can also, with this type of geometry, we can define a quantity that's quite important for imaging is the magnification. Okay. What the magnification is really telling us that if I have a real-world object, what is essentially the geometric scaling onto my sensor? Okay. Or my detector. Okay. So if something's 1 meter and I want it to exactly close in my 1 centimeter sensor, then I would need a magnification of, I would need my magnification of 100 or 1 over 100, depending on which part of the world you're from. Magnification is either big or small, depending. I'll show you in a second what we're going to use here. M greater than 1 is a microscope, so that's a small object onto a large frame. So I'm going to take something tiny and put it onto a big sensor. That's M is greater than 1. A telescope is M less than 1. I take a large object and put it on a small frame. So M greater than 1 would be normal. I have a sensor, a camera sensor that's 35 millimeter, and I want to take an image of that blackboard or this entire frame here, and I want it all to fit on there. That's M much less than 1. Okay. In general, that's the magnification we deal with. We deal with M much less than 1 for most of our imaging, and we work really hard to approach M is equal to 1 for some of our experiments. Okay? So again, we can combine the thin lens equation with our definition of M, and now we end up with some equations that give us the relationship between the imaging distance, again, the distance between my detector, okay, and the lens, magnification, the focal length of the lens. So let's look at an example for imaging. One thing I would encourage you all, if you don't already have this article in your library, this was a review article by Noel Clemens, Flow Imaging. It's an excellent piece of work. It's got the majority of the information you need on like optics, imaging, kind of a cursory overview of a lot of techniques. So it's wonderful, wonderful article to have in your collection. Okay, let's say we have a camera. here's our camera sensor, here's our lens, and this is a portion of a field of view, right? So laser is going in, and this is what we're trying to transfer that information onto our camera sensor. So let's say our cameras have pixel delta x times delta y. What we can now say is the regions in the flow characterized by different delta y, okay? Del x, we'll call this, I'll call these the pixels del x and del y, and the flow delta x, delta y. So delta x is del x over m, delta y is del y over m, and then here's the relationship between the entire size of the image, the sensor, and the field of view. Okay, so the magnification tells me for my given sensor size how much of a field of view I can put onto that sensor. Okay. The solid angle subtended by the lens is defined in this expression. And the camera F number, which is the focal length over the diameter of the lens, ends up being related to the solid angle. Okay, so what we're doing is we're trying to just connect a lot of these geometric aspects. So what this allows us to do now is say how many photons can we collect? Okay, so let's look at this. Let's assume we have a field of view illuminated by a laser with height YL. That's what this is. Okay, so that's the height of my laser coming through. You've set it up with some set of optics. It has a thickness delta Z and a laser fluence FL, and this we'll just call the laser fluence here. We'll assume that everything's uniform, so it's going to be laser pulse energy per area of the laser sheet. Okay, the total number of photons collected by each pixel can be written as this expression, which is the fluence over Planck's constant and the spectroscopic frequency, or volume, scattering cross-section. This is species dependent. This could be scattering cross-section. It could be a version of an absorption fluorescence cross-section. We can just call it kind of a generic process. We have the number density of the scattering medium. We have the collection lens, and then we have the transmission efficiency of the lenses. Okay, so if we assume that the laser sheet is uniform energy distribution, that means it can be approximated as just the energy of the laser divided by the height of the laser and delta Z. Okay, so if we make that assumption, that means we can now write the number of photons that are collected, photons per pixel, SPP, in this expression. Okay, I don't need to read them back out, but now we're getting our magnification related to our pixel size. So this equation right here can tell you how many photons per pixel that you can collect in the context that no matter what you do with your laser, your optics, your movement, that the laser sheet does not change size. Okay? So if it's for one set of magnification, it's covering up the entire sensor. As I move my camera back and I get a different magnification, now it's only covering only a portion of those pixels. Okay, so your laser sheet does not change physical size. When you do this, this equation shows as the magnification heads towards zero, the photons per pixel, your signal increases. That is, you collect more photons per pixel as you move the camera further away from the object plane. So first of all, we say, is this counterintuitive? Because as the magnification goes to zero, the collection lens goes to zero, the collection angle goes to zero, so you think, okay, I'm not collecting a whole lot of photons. But the actual physical region of which you're collecting photons from, delta X and delta Y, increase. So that each pixel on your camera is collecting more and more light from a larger region of the flow. So essentially you can think about in the limit that I keep making my magnification smaller and smaller, my entire laser sheet fits on one pixel, right? And so all that light is coming through. So that's why that equation works. But let's look at a slightly different version. Let's say that now as we change our magnification, the laser sheet is increased to accommodate the field of view. Let's say I always want my entire sensor covered. So as I change the magnification smaller and smaller, such that I'm imaging a larger field of view, I'm making my laser sheet larger and larger as well. Okay? All right, so let's assume that the laser sheet can be just equal to the size of your sensor. That's what we just said. And then that allows us to say that's the number of pixels times del y over m. Okay? These are just geometric expressions. This is the number of pixels in one column array. Okay? So again, we're assuming that the laser sheet is always at the field of view y naught. Okay? So we change the magnification. We keep making our laser bigger and bigger. So now we get a different expression for the total number of our photons. Okay? It's still a function of m magnification, but now we can see the magnification actually lies in the numerator, and we have this m over m plus 1. So we can actually see some kind of useful observations that kind of give us the characteristic of signal collection is the signal depends on the total number of incident photons. That makes sense. The more incident photons I get, probably the more signal I'm going to get. But the signal is independent of laser sheet thickness. Okay? So if I have a tighter focus, my fluence increases, but the number of scatters is going to decrease, right? If I have a certain amount, imagine I have scatters uniformly distributed in a volume. As I make that volume narrow and narrower by getting a tighter focus, I'm going to hit less and less of the scatters, okay? So the fluence goes up, but the number of scatters goes down, okay? So as NP goes up, right, as number of pixels, that's really what that's saying is that smaller pixel size for a fixed sensor, we get better spatial resolution. So imagine I have a sensor that's 1 centimeter squared. As I add NP, that means that each pixel has to get smaller, right? I have to fit more pixels. That means that each one, I'm getting better resolution potentially on my measurement. But the signal per pixel is going to go down as each one's going to collect less light. Okay, so we can see that as NP goes up, signal goes down. So really, this is the first way that we can start to see that there's kind of this inherent balance between spatial resolution and signal collection, which will turn out to be a signal-to-noise ratio. Okay? So it's very difficult to get great spatial resolution, keep increasing our spatial resolution, and keep increasing our signal. It's just fundamentally not allowed. Okay? And then we can see this expression that the photons per pixel scales as m over m plus 1 squared, such that our signal in this context is actually maximized at m is equal to 1. Any telescoping or microscoping results in a relative loss of signal. Okay? And then also what we get here is that the signal goes as 1 over the f number squared. So low f number lenses lead to large increases in signal. So you'll have on your lens an F number, and again, the amount of signal that as you go from, let's say, 5.6 to 2.8 to 1.4. You've played around with this before, though you know that the light goes up dramatically. It goes up essentially as the square of the F number. So again, low F number, very high increases in signal. But one thing that we'll talk about in a little bit, low F number leads to a very small depth of focus. Okay, so it becomes much more difficult to focus your image as that F number goes up. Okay, it comes down. Okay, now let's move on to physical optics. Okay? Physical optics considers the propagation of electromagnetic waves and the interaction of these EM waves with matter. Okay? We can see in this image, we have an electric field E here, we have a magnetic field B, and we have a propagation direction. And we'll prove why these things are all orthogonal one another. Okay? So light is an EM wave, and we need some definitions. Okay? There's a host here. Let me point out a few of them. Obviously, E is the electric field. H is the magnetic field. B is the magnetic induction field. B is related to H via mu, which is the magnetic permeability. J is the electric current density. D is the electric displacement field. And D and E are related through the electric permittivity, which we'll actually call this also the dielectric constant soon. And then we have charge. We have essentially the current, how it's related to the conductivity in the electric field, and then we have charge density. Okay? So these are all things that perhaps you saw, again, undergrad, those first couple years of physics, and again, in terms of electromagnetic theory. So what we have here is mu, which is the magnetic permeability. This essentially accounts for the magnetic properties of the medium in which the magnetic field is established. And again, this epsilon, which is the dielectric constant in the medium, we'll see the importance between epsilon and mu in establishing these two fields and allow them to essentially allow them to sustain one another. Yeah, here we go. All right, so epsilon and mu, they sustain one another, and we get EM propagation. Okay, so let's talk a little bit about what we have. We don't spend too much time, but in the late 19th century, Maxwell compiled the known laws of electromagnetism. So actually, what was kind of cool about this is that he was responsible for connecting the fact that light propagation is governed by electromagnetic principles. Prior to Maxwell, it was really light was considered as a different type of medium. It wasn't considered to be the same as EM, electromagnetic waves. And he made a couple modifications that will show that allows us to use optics in light propagation through electromagnetic principles. Okay, so here's equations. Again, you have them. We have Gauss's theorem. Okay, again, we have del dot D is equal to rho. We can write all of these. That's Gauss's theorem. 10, we have del dot B is equal to 0, sometimes referred to as the no magnetic monopole. That's really any closed loop around a magnetic field contains no net magnetic charge, or it's magnetically neutral. We have Faraday's law. Okay, what you see here is we have a time change in the magnetic field will induce an electric charge. Okay, if you go back to the previous equation on what electric field is proportional to. And it really, you got an action by B induces a reaction in form of electric current. Okay, so again, we're going to get a corresponding current loop coming from a time rate of change in B. And then we have Ampere's law plus a modification. This is the so-called displacement current added by Maxwell. We had Ampere's law, which was the original law. If you look at this, this is the curl, so if we take the divergence, we essentially have the divergence of J has to be equal to 0, right? Because divergence, the curl is equal to 0. And so what that really says is divergence of J, if divergence of J is 0, that would imply that the total flux of the current out of a system, of a closed surface, is 0. And the flux out of a closed surface is the decrease of the charge inside, right? So we have a certain amount of charge. The flux is, if there's a net flux out, the charge has to decrease. But if we say there's no net charge, no flux out, then there can be no change of the charge inside. But we know this is not true because charge can be transferred from one place to the other. So what happens is Maxwell added the modification, which is the displacement current, such that we can have the transfer of charge. So it's a modification to Ampere's law. So again, these are kind of the basis of Maxwell's equations. And so our whole idea from using these is we want to know how light is going to propagate, so we need a wave equation. Okay. So the first thing is going to assume that all light and optical interactions are electronic, such that we can get a solution for E that's independent of the magnetic field. Okay. This solution has been done and detailed by Feynman and co-workers. Okay. And these ends up being, this are sort of the solutions of the equations. This is with assuming that epsilon is constant and rho and sigma is equal to 0. Epsilon is constant is just a uniform medium, that's all. And rho and sigma equal to 0 can either be free space, so it's vacuum. It can be an electrically neutral medium, or it can be a medium where the charge dissipates faster than the characteristic wave time. All of those are fine for setting rho and sigma equal to 0. And when you do that, from those set of equations, you get these. Well, if you look at these are just wave equations with wave speed equal to the square root, or the inverse of mu naught epsilon naught. So this is your classic just wave equation. And I wrote it in the generic U. Okay. So let's get a solution. The solution must have this form. E times f of t, so this is a time-dependent portion. R is a position vector. So we have to have a position portion that's position vector, part that's temporal component, and then we have a position vector that can just written as X, Y, and Z, and they're, again, they're different component factors. Okay? All right, so that's the way that we always say there's a lot of work. There's a squiggly line with an arrow, and we get to, this is the solution. Again, that's not really what we're going for here, but what we have is that the electric field is the real part of this expression here. Okay, and within here, the components that we're interested in is that omega is the oscillation frequency of the electric field. Okay, E naught is the amplitude of the electric field. K is the propagation vector. Okay, and phi is a phase angle. And for most of our applications, that'll be unimportant. Okay, but then we do have this. This is the solution. So what we can see is that the electric field oscillates with an amplitude of E naught, okay, and with wavelengths that have magnitude over, what is this, 2 pi over k. So their wavelengths have magnitude of 2 pi over k. So this is the solution describing the motion of a set of plane waves. Okay? Now the wave equation is linear, so we can get complex solutions by combining solutions that have various values of E naught, K, and omega. Okay? And so this is the foundations for physical optics solutions. So let's do a little bit, let's substitute that our 15, our solution into Gauss's theorem. And if you look at that, if you put in the fact that del dot E is equal to 0, you end up putting that solution, you get I times K dot E has to be equal to 0. And so what this implies here is that E and K are perpendicular. Okay? And you can also show that the magnetic field is also perpendicular to K, and that the magnetic field is perpendicular to B. So all three of these vectors are mutually perpendicular. And that's when you end up with this schematic here. You have a propagation direction, and then now you have the electric field and the magnetic field that are perpendicular to each other and along the direction of propagation. Okay? So what happens is E and B are restricted to a plane that's perpendicular to the direction of propagation, and that's why they get denoted as a transverse electromagnetic wave. So we call these TEM waves. But as I'll talk about in a minute, they only have to be perpendicular, but they can rotate at any angle. Okay? So how is the propagation of the E field different from something like an acoustic wave? Acoustic wave is also described by a wave equation with speed c. Well, the acoustic wave amplitude is a scalar, the propagation is a vector, but the electric field here, the amplitude is vectorial, and this turns out to be quite important, and it distinguishes this solution from the wave equation. This is what's connected to a concept that we call polarization. Okay? So the components of E naught represent the optical polarization, so now we're starting to bring it back to something that's probably a little bit more realistic. For you, like in the lab, you'll work with things that are vertical, horizontal, or S&P polarization. These are just the components of the electromagnetic field. And this is the optical polarization. Okay? As we said, E has to oscillate normal to K, but it can be at any angle in the plane wave, right? So we're going to keep this in mind, that we can, if we have a propagation direction, let's say along my arm, we can turn E and the electric and the magnetic field at any direction. Okay? So what we can do is we can decompose any polarization state into two states. 1D propagate, okay, in two states. And this can be in 3 dimensions, but that's really hard to visualize. So let's do a 1D example. Okay? So again, instead of having our general position vector, we have Z here, and then we have just K naught, which is the magnitude. What I really want to point out for this is that this E naught, this vector, then is now decomposed into E naught X with unit vector X and E naught Y. So right now we can call these X polarization, Y polarization. Okay. So really the electric field here is the outcome of the superposition of two independent fields. And that's important. So since we can decompose it in two states, our actual electric field is the superposition of two independent polarizations. Okay? Now, for each field, each time we have a laser, which is an electric field, we can decompose it in two states. Their frequency and the propagation vector has to be the same. But neither the amplitude nor the phase angle have to be the same. Okay? And this is why you can have generic elliptical polarization. And we'll talk about this. The energy carried by one component is independent of the other. So they don't have to have the same amplitude. They don't interact with each other. Each component is independent of the other. Since they're oscillating at the same frequency, this is the wavelength, right? Their oscillation frequency is what we determine as spectral frequency. So they're spectrally indistinguishable. You can't tell the two polarization components apart. Okay, they're both, if they're 532.xxx, they both are that. Okay? But they can be separated by optics that are sensitive to polarization. These are birefringent materials. Okay? So, in general, what does E describe? If we say we have this general case of it propagating along an axis, well, it's an ellipse on a plane. Okay? So let's look at what optical polarization is. It's an ellipse on a plane perpendicular to the direction of propagation. If we have propagation going this way, our general case is an ellipse. Why is an ellipse? Well, we can have two components of polarization, and they can be out of phase. And so therefore, they're moving down like almost a helical motion, such that when you look at it and kind of across, you get an elliptical position. Now, of course, our general elliptical case can be written in terms of special cases of linear polarization. Here's a case where we're even missing a component. It's just, this case is just Y polarization, and therefore phase shift has no meaning if we only have one component. Here's a case where they have the same magnitude in phase shift. This is still linear polarization. It's just 45-degree linear polarization. Here's a case where their magnitudes are not the same, and their phase is not pi over 2, so you get elliptical polarization. This is the general case. And then, assuming that their magnitudes are the same and they're out of phase, or the phase shift is just pi over 2, or an integer of pi over 2, you get circular polarization. So the reason I bring this up is this is very important for a lot of optical diagnostics are polarization sensitive. We're going to have to talk about this. And a lot of your optical components are polarization sensitive. Okay, now let's look a little bit at energy of electromagnetic waves. This is kind of where we're going to be able to define our quantity of flux. Let's consider the analogy of the first law of thermodynamics. Many of you are familiar with this. We have Q dot and W dot. This is the heat transferred across boundaries, the work performed across boundaries. We have the specific internal energy. Okay, that's the energy per unit volume. Okay, and then we have the energy flux across the boundaries carried at velocity v. So this is the first law of thermodynamics. Applying a divergence theorem, we end up with this. Okay, laser diagnostics class, we're not going to do anything else with the first law. But we want an analog with sort of propagating electromagnetic fields. Okay, so the first thing we're going to do is we seek to find kind of an analog for each one of these terms. And so the first one, Q dot, we're going to ignore. We're going to assume that we have an adiabatic system. So let's forget about that. But now we have the rate of work done by electric field is J dot E. That's the work done by electric field on the charges. The analog to the internal energy, which is the energy stored within a unit volume, is what we refer to as the stored electromagnetic energy density. And if you work out the units or do a little bit of manipulation of the other equations, you can see that it has to be essentially epsilon over. It's essentially epsilon E squared plus mu H squared, and the twos just come from proper manipulation. And then, but what we really want to look at is the last term. The reason we did this is to get the last term in the first law of thermo represents an energy flux across the boundary of a volume. So what we want is the energy carried by the EM wave as it propagates. This is what you care about. This energy flux is something that's referred to as Poynting's vector, and it's E cross H, okay? And really, what is this? This is a radiance, okay? This flux is interpreted as the light intensity. This is the intensity that's being propagated by your EMA. That's the intensity of either your laser beam or the light that's emitted, okay? All right, so if we combine all these things together, we get an equation that's very similar to the first law, okay? So again, we assume the medium is adiabatic. You end up with this expression. Well, we can go one step further and say, okay, we don't have any electrostatic charge. J is equal to 0. We established that earlier. And again, if we have negligible absorption, well, if we don't absorb any photons, then what happens? The internal energy remains unchanged, right? And what this tells us is J dot E goes to 0, this internal energy goes to 0, and del dot S is equal to 0. So this means that their radiance is constant as it propagates through the medium. And this also kind of connects some stuff you already know, that if I'm not absorbing photons, I don't lose any of my irradiance. But as I start to absorb, as I start to change the internal energy, I lose some of my irradiance. Okay? So we can also combine some of these equations. Again, that's not important. But what's important is that we end up getting the magnitude of the magnetic field vector relative to the electric field vector is proportional to the square root of epsilon over mu. And again, I discussed a little bit earlier, that's these quantities that sort of sustain the fields. Now, we can take this expression, put it back into that expression of Poynting's vector, okay, E cross H. If we integrate over a time period that's long relative to electric field cycle, but very short to a characteristic time of illumination, okay? So think about this, long compared to the cycle frequency of the EM wave, but very short compared to something we care about, right? Microseconds, nanoseconds even. If we do that, we actually end up with this expression here. And this relates the irradiance to the magnitude of the electric field. And so for a TEM wave, the direction of light is coincident. But what we also see is that there's a quadratic dependence on the electric field components. Okay? So we can see from here that the TM wave is going to propagate, the light irradiance goes in the exact same direction as the propagation direction. And then the intensity of our wave is the square of the electric field. Okay? And we'll come back to this. Okay? Now, all of that is EM propagation in a vacuum. Now we need to understand what happens when light propagates through another medium. And this is the basic for any diagnostic. Okay? We have to introduce a concept called the material polarization, okay, also called the polarization. And we can't confuse this with the optical polarization. Okay? So it's unfortunate they have the same name, but material polarization is not the optical polarization. So the material polarization is the collection of active polar molecules within a unit volume. If you remember from chemistry what a polar molecule is, it's when a polar molecule, you have the atoms in the molecule, and each one of those essentially has a level of electronegativity. And it's the net, it's the distribution of electrons when they covalently bond these atoms together. So they all have electronegativity, and when they're bonded together, it depends kind of how the net distribution ends up. Okay? So think about water. Water is a very polar molecule. I have two H's and an O. O is a lot more electric negative than H. When I put them together, the O kind of sucks the negative charge up to the O sides, and you're left with sort of all these protons sitting over on the hydrogen side. When you do that, you have a polar molecule. But if you put something like O's and N's together, we have similar electronegativity, that change is not too great, and that ends up creating a nonpolar bond. Okay? So the polarization is then now we have a volume, and we have a certain level of polar molecules within a unit volume. So we call this polarization vector is the summation of the dipole moments, which is our total density of active dipoles. And then we have their charge and the distance between these two molecules. Okay? Bear with me. So right now we're saying, okay, it's kind of the total amount of the polarizability, and that's what we're going to talk about. Well, certain molecules like nitrogen and oxygen may be nonpolar, but they certainly can be induced with an electric field. And that is the basis for pretty much every laser diagnostic, is the fact that the electric field induces a essentially a polarizability in the molecule. Okay. So when an electric field transmits through a medium, the material polarization can be induced. So it can already be a polar molecule or it can be a nonpolar molecule. And we describe this through this relation. So we have epsilon naught times chi and E. And chi is the electric susceptibility of the dielectric species. And really what the susceptibility is really it's a material parameter represents the ability of a dipole, think about dipole, a species, to respond to polarizing electric field. Some will be resistant, some are happy to play along. That's how you can think about it. So it's just a material property. Okay? All right, so let's go back to our displacement vector D is equal to epsilon E. In the absence of a polarizing electric field, this must be equal to D epsilon naught E, right? This has to be the quantity in free space. Now, if we add electric field or we have some material polarization, we can then rewrite this expression in this manner. And just with some manipulation, we rewrite the equation in this way, such that we can now define the electric permittivity or the dielectric constant in a medium equal to that of free space times the electric susceptibility. Now, the reason we write that is that we can rewrite Maxwell's equations now with wave-matter interactions, such that everything is now, instead of being described with an epsilon naught, it's described with an epsilon, and it has this electrical susceptibility embedded in there. That gives you a new wave equation, a new wave speed, and now a method to calculate the index of refraction with a medium. The index of refraction is the square root of 1 plus the electric susceptibility. Now, what we can actually then write our wave equation, I think, in kind of a neat way. We do all of this. You bear with the progression of this way we write the equation, and we end up with this final expression here where the left-hand side looks very familiar. It's the wave equation in a vacuum, and the right time is a source term. And this is due to the material polarization. This is actually due to the influence of the electric field. Okay, so when I have so we have our vacuum, and then we now have a source term due to material polarization. Okay, but the material polarization comes from the interaction of the EM wave and the material. So what does this mean? So bear with me, and if you have any questions, make sure you ask. In between molecules, if you zoom in, if you think about it, there's basically free space in between molecules. And so what happens is the electromagnetic field actually propagates in that free space. But it doesn't propagate over the molecules no matter what we like to say. What actually happens is it interacts, and when it interacts, it sends another wave. That's the source term. It sends another wave that then propagates in free space, and when it interacts with more dipoles, it keeps sending a wave. So sometimes this is referring to propagation, and then it leapfrogs it. Well, it doesn't leapfrog, it actually sends another wave. Okay? So that's actually how an EM wave or a series of waves propagates. You have the original EM wave, first time it encounters a dipole, it actually propagates another. It's technically a separate wave, but it all has the same characteristics. So it hits a molecule, and then it propagates a wave. Okay? All right, so now let's assume that our propagating light wave has very strong electric field. In this manner, a nonlinear material interaction can occur. So if you look at this, we have something that's now referred to here as what's going to be referred to as the nonlinear polarizability. But the first term is just what we had. That's the linear polarizability. And again, now what we have are these nonlinear susceptibilities, okay, which these are just material constants describing various nonlinear optical interactions. All this is saying is that as you think about this, as we crank up the electric field, like just really crank it up, which means taking a laser of energy and just focusing down, get really high irradiance, we start to end up with these nonlinear interactions. We can have our original linear interaction, but then all these higher order interactions. Then we get a different equation, and then we have a new source term. But the really interesting thing about this, and this comes back to cars, is this source term generates a new wave. Remember, I just described that we propagate in free space, we hit a molecule, and we propagate a new wave. For the linear, it has the exact same characteristics, right? But now when they're nonlinear, they do not have to. They can go in a different direction. They can have a different wavelength. There's a lot that's embedded in this higher order term. they do not have to have the same characteristics. Only the linear wave is the same as the original wave. So think about cars, I said generates through this four-wave mixing, I said generates another wavelength in a different direction and in a different wavelength. That's because of the nonlinear interaction. Okay. All right, so this is the final slide on this. So just to give you an idea, absorption in single photon fluorescent processes are what are called Chi-1 processes. Those are linear processes. And then a lot of these other kind of harmonic, like single harmonic generation, any type of these crystal generations, some frequency generation, different frequency generation, optical parametric oscillation. These are Chi-2 processes. CARS is actually a Chi-3 process, meaning it uses the third order susceptibility. Again, make sure you don't confuse the relationship between optical signal and the intensity of the instant radiation. Let me when I say linear and nonlinear. Techniques are characterized as linear or nonlinear based on the relationship between the optical signal and the incident intensity. So techniques that exhibit a quadratic or higher dependence, the signal on the input, are nonlinear. So as an example, the amount of susceptibility in the interaction doesn't make them linear or nonlinear. For example, spontaneous Raman scattering is linear. You send us, for whatever amount of photons you send in, the signal you get about is proportional. But the light matter interaction is nonlinear. Okay? It uses these higher order processes. Okay? And that's it for lecture 2. Only 2 minutes behind time. Questions before we take another break? Yes? What's the... so basically the susceptibility, right, will go as the electric field, right? So everything you can write that as an infinite sum. They just, as the intensity field is low, they're just negligible. So they haven't. It's an infinite sum, right? But what happens as the electric field becomes higher and higher, those actually have meaning and value, right? And so then also every wave has. You can think about it has all possible wavelength and direction solutions, but when that susceptibility is a low order, those are also negligible as well, and they die off. So really what I'm talking about is more from a pragmatic, that only as the intensity increases do you actually see these effects, right? So they're sort of always there. It's just, think about they're completely meaningless when the electric field is at low enough intensity. Okay? Yes? So you meaning the omega or the wavelength of the... So let's go, that's a good question. Let's take a look at this. Let's go back a couple of slides. Oops. That's not where I wanted to go. Okay. All right, so we have our solution of the let's see, where do we want? Okay, I'm trying to kind of connect a few things. The solution to the electric field is certainly frequency dependent, right? And the irradiance is a function of E. But it's only, that light-matter interaction only depends on the amplitude, E naught. So to answer your question, it does not, it depends. The answer is yes and no, but the way that I think you're asking is no. It really depends on the amplitude, but the solution is certainly frequency dependent, okay? So that's why I'm trying to make sure I don't hedge. We can talk about in detail after we come down, but it's really what you're looking to in terms of, it's the amplitude, the E naught component is the most important for getting these kind of higher order terms to come up, okay? Does that answer your question? I think I know what you were asking. I just didn't want to. Okay. Other questions? If not, it's 4:25. We will take our 15-minute break. so 4:40, and then we'll just end at 5:40.